Earth Systems 3209, Unit 5, Earth's Resources. Reference for this unit can be found in the textbook in Chapters 21, and also in Appendix A and B of the Curriculum Guide. Unit 5, Topic 3.4. This topic will look at the different types of petroleum traps. We will focus on identifying and describing the types of petroleum traps, and identifying each type of petroleum trap using diagrams, and also relating how density influences the relative position of petroleum in an oil trap. When we look at the different types of petroleum traps, several geologic structures may act as a petroleum trap, but all have two basic conditions in common. The first condition, porous permeable reservoir rock that will contain quantities of oil and gas that make it worth drilling. The second condition found in all petroleum traps is impermeable cap rock that traps oil and gas, preventing it from escaping to the surface. This presentation will look at the different types of petroleum traps, including an anticline trap, a salt dome trap, a fault trap, and a stratigraphic trap. Information on these different types of petroleum traps can be found in the textbook on pages 603 to 604. The first type of petroleum trap is referred to as an anticline trap. Information on this type of trap can be seen in your book on page 604. If a permeable rock layer like sandstone or limestone is located between impermeable rock layers like shale, and the rocks are folded into an anticline, that is an upfold, oil and gas can move upward in the permeable reservoir rock, and it can accumulate in the upper region of the anticline. We see this in the diagram below. Here we have two impermeable rock layers, outlined in gray. We also have in between the two impermeable rock layers a permeable and porous rock layer, which we call the reservoir rock. In the reservoir rock, liquids can pass through freely through the pore space of the reservoir rock. And in this case, water, oil, and gas has moved through and accumulated within the reservoir rock. According to density, water will be located beneath the oil, which is located beneath the gas. And this is the structure that we see in all oil traps. We see water, which is higher density, located below the oil, located below the gas, which has the lowest density. And this pattern can be seen in all different types of petroleum traps. The second type of trap is called a fault trap. Information on fault traps can also be found in page 604 in the textbook. If faulting can shift permeable and impermeable rocks so that the permeable rocks always have impermeable rocks above them, then oil can get trapped. Note that both normal faults and reverse faults can form this type of oil trap. In the diagram below, we see that both normal fault and a reverse fault can form a fault trap, where it traps oil and gas. On the left side of the diagram, we see a normal fault. Here, we see the impermeable rock layer move down with the hanging wall in relation to the impermeable rock layer below the fault line, which is located within the footwall. Also at the top of the permeable and porous rock layer, we see that the impermeable rock is also connected with the impermeable rock on the other side of the fault. This prevents the oil and gas from moving upward to the surface, and it actually traps the oil in the upper part of your reservoir rock. So this would be an example of a normal fault where oil and gas is trapped. On the right side of the diagram, we see the opposite type of fault. We see a reverse fault. And in this case, the impermeable rock, which is your cap rock, moves upward with the hanging wall in relation to the impermeable rock located within the footwall. Again, at the top of the permeable rock layer, we see an area indicated here, where the impermeable rock prevents the oil and gas from moving upward toward the surface, thereby trapping the oil and gas within the reservoir rock. So in both types of traps, oil trap here with a normal fault and the one on the right with a reverse fault, both demonstrate the sequence of water overlain by oil overlain by gas. And this is according to, again, densities. The third type of petroleum trap is the salt dome trap. Here we see the salt that has moved upward through the earth, punching through and bending rock layers on the way to the surface. Oil can come to rest right up against the impermeable salt, which makes the salt an effective trap. If we look at both sides of your salt dome, we see that we have impermeable rock both below and above the reservoir rock. Within the reservoir rock, we see water overlain by oil, which is further overlain by gas. The the salt dome itself prevents the migration of the liquids from hitting the surface, and it traps the oil and gas within the permeable and porous reservoir rock. So in this case here, the salt dome, as it moves up to the surface, pinches off the porous permeable reservoir rock, and oil and gas can be trapped on the side of the salt dome. So this would be an example of a salt dome trap. And the fourth type of petroleum trap is called the Limestone Reef Trap. A limestone reef trap is a type of stratigraphic trap. When coral reefs become buried by other impermeable sediments, they can form excellent oil sources and reservoirs. In the diagram below, we have a permeable reservoir rock overlain by an impermeable cap rock. And in these stratigraphic layers, the oil and the gas can get trapped by the impermeable cap rock that's located above. Further to the different types of petroleum traps, we need to look at the properties of the materials that make up the trap. In this case, the water, oil, and gas would have different densities. And density is the physical property that distributes petroleum within the reservoir. Water is more dense than oil, and oil is more dense than gas. Therefore, when drilling into a petroleum trap, gas is encountered first, followed by oil, and followed by water. If we look at the diagram below, and we drill a hole straight down through into the different types of rock layers, we will notice that we would encounter gas first, followed by oil, and followed by water. And this is because of the property of density. Some reservoirs may have all three components, whereas some other reservoirs may only contain two components, or some reservoirs may only contain one component. But in most reservoirs, we see water at the bottom of the reservoir overlain by lighter density oil, which is then further overlain by the lightest density of gas. Let's look at some examples. First question reads, which petroleum trap will be formed by a simple fold? If we look at a simple fold within sedimentary layers, we generally see two parts of a fold, an anticline followed by a syncline. An anticline is an upfold within the sedimentary layers, and the syncline is a downfold. When we look at an oil trap would be formed in the upfold of a folded sedimentary layers. So the answer to the first question will be A, anticline. The petroleum trap that could be formed by a simple fold is called an anticline trap. Second question reads, which limestone reef trap belongs to which type of petroleum trap? So when we look at the limestone reef trap, it is basically a trap that forms within layers of sedimentary rock. And layers of sedimentary rock forms a stratigraphic trap. So our answer to the second question would be D. A limestone reef trap is an example of a stratigraphic trap. Example number 2. Based on the diagram below, which is the correct match between the force and the petroleum trap produced? In this question, we have 4 choices. The forces could be compressional, and the petroleum trap could be a fault trap. We also could have compressional forces with an anticline trap, tensional forces with an anticline trap, and tensional forces with a fault trap. If we look at the diagram to the right, we notice that we have a fault line which is located by the dark line that moves downward to the left. This fault line would separate the hanging wall from the footwall. And if we draw, as we did in Unit 4, a stick man across your hanging wall and footwall, we notice that the hanging wall will move downward with respect to the footwall. And this is primarily due to tensional forces which cause the rock units to move apart. So in this case, we see tensional forces. And tensional forces that cause the rock units to move apart would form a fault. And in this case, the example of the fault would be a normal fault. So if we go back and look at our choices, we notice that the type of force would be tensional, and it also forms a fault. Therefore, our answer to this example would be D. Tensional forces which would cause a normal fault, and the oil would form in the upper part of the reservoir rock along the normal fault. So the answer to this example would be D. Your turn. Take the time and complete the following question. You could pause your recording now to prepare your answer, and the solution will be on the following slide. The question reads, which sequence is correct from highest density to lowest density? When we look at the formation of petroleum traps, the materials that get trapped separate according to density. And previously stated, the density will go from the highest dense material on the bottom to the lowest dense material on top. So the sequence that we would see in a petroleum trap, we would see water overlain by oil, which is overlain by gas. So therefore the water would be the highest density and the gas the lowest density. So the sequence that correctly answers this question would be D. Water, oil, gas, from highest density to lowest density. Let's look at the overview of points covered in this presentation. This presentation focused on the different types of petroleum traps, and they include an anticline trap, where we see folded sedimentary rocks, and folded sedimentary rocks would form an upfold, which is called an anticline, and within the anticline we would see a pattern of water overlain by oil, overlain by gas. That would form an anticline trap. We also looked at a fault trap. Fault traps can either be formed by normal faults or by reverse faults. And in both examples, the faults would be formed where the impermeable rock layer would prevent the oil and the gas from moving upward toward the surface. And they would be found within the reservoir rock that is bound by a fault, and that being a normal fault or a reverse fault. The third type of petroleum trap was a salt dome trap. And the salt dome migrates upward through different rock layers as it migrates towards the surface. And in doing so, it can pinch out some of the reservoir rock. And because the salt dome is impermeable the materials such as oil, gas, and water that moves through the reservoir rock would actually get trapped up against the edge of the salt dome. So again, in this type of petroleum trap, we see water overlain by oil, overlain by gas, and it is bounded by the salt dome. And the fourth type of petroleum trap we studied was a stratigraphic trap. And the example of a stratigraphic trap in this case will be the Limestone Reef Trap. And within the Limestone Reef Trap, the limestone is a good reservoir rock and source of petroleum. Therefore, if overlain by an impermeable rock layer, it could possibly trap the oil within the carbonate or the limestone. So these are your four different types of petroleum traps that was looked at in this presentation.